what happens if you had used improved Euler? If you have improved Euler, modified Euler and improved Euler, which I have already implemented and plotted here, and of course, you must also implement and plot it and compare these things, and also for different values of dh, you see that of course, at small values of x you have a good agreement, hardly surprising. Even Euler was giving a good match for small values of x, but at large values of x, both modified and improved Euler is much better. You see that this is nearly matching, right, much better than Euler. There is no, I mean, hardly any comparison, and of course, I have maintained dx equal to 0.02 to be able to compare, right, which is for Euler was this black curve. But let us see, let us blow up the data and see whether there are any deviations, at least here. As you zoom in on the data, this is your blue curve, which is the theoretical analytical tan x, and modified Euler has results closer to the analytical value, but improved Euler is even better, right. It is going more closer and closer to this thing with the analytical value, but still there are deviations. Deviations are being picked up as tan x rapidly goes towards infinity. Not good enough. Now, the next thing you will be learning is the Runge-Kutta method, and if you use the Runge-Kutta method with the same value of dx, in this purple curve is the data, is the Runge-Kutta RK4 integration scheme, which we shall discuss. You see how good the match is with the analytical one, even at 1.54. You can also extend it to 1.55 as I was saying it to the lectures, but definitely this Runge-Kutta is much better, no doubt, than the Euler, keeping dx the same. This is the Euler, this is the modified Euler, this is the improved Euler, and you can see for yourself what is the value of the Runge-Kutta one, with it really matches very well, much better than the others as x approaches 1.57 pi by 2. Of course, I have not drawn for pi by 2 exactly, because it will be infinity, I can plot it, but even close sums, even at x values close to 1.57, it is significantly better. So, next let us learn about the Runge-Kutta method, which is distinctly much better, and typically for real problems you use the Runge-Kutta method for solving differential equations, right. Euler's methods is just an introduction to see how we are adding more terms to increase the accuracy, starting from the Euler method. Next, so that is what we discuss next. So, coming to the Runge-Kutta method, to discuss what is the algorithm of the Runge-Kutta method. So, we will be discussing one version of it, which is called Runge-Kutta 4, RK4. Why 4? Because though I will not be talking about the derivation of it, but this RK4 method is accurate to orders of h to the power 4, h being the integration dx, I mean the step size basically. So, if you take a small dx, so say dx equal to 0.01, then the accuracy of your solution, how accurate it will be, how much will it match with the actual solution, will be 0.01 to the power 4, right. So, that is the accuracy of it, and you see that in the Runge-Kutta method, this is significantly more accurate than the Euler method and the improved Euler method, where the accuracy is order of h square, right, which is the where h is the step size. Now, before we discuss the Runge-Kutta method, let me tell you what is the principle of it. I mean, what is the broad idea of it rather than the steps. For that, let us look back upon the improved Euler method, okay, and this was y and this was x, and you have to integrate out dy dx equal to f x y, and suppose this curve is the y curve, right, and you have to start from some x 0 and y 0. So, you have to tell the range of the over which you are going to integrate to get the solution to the differential equation, and at x 0 and y 0, suppose you can calculate the value of f x y. Now, what you did in improved Euler was you did a simple Euler step and updated the value of x 0 to x 0 plus h. Similarly, correspondingly you updated the value of y. With this, at this updated point, you calculated f 1 again, right, so which is a different point, and then finally to calculate the actual value of y 2 at the next step, you use the average of this point and this point, right, the average of these two slopes dy dx equal to f x y. So, the you took the average of this slope and this slope, right, and then got the actual update to the next value. Now, in Runge-Kutta, what you do is use the slope or f 0, so as to say at this point. Moreover, calculate the slopes at multiple points between the interval of x 0 and x 0 plus h. Okay. So, you try to have a better and better estimation of the value of the slope at different points in the interval. And remember, RK4 is accurate to h to the power 4, right, 4 times, 4 orders. Hence, you can easily take larger step size without compromising the accuracy of your calculation. So, you can take larger step size, and if you have a large step size, then over that step size basically the value of f x y is going to change. Hence, you are trying to have an average more accurate estimate of this value of f x y at different points over the interval. Take an average, take a weighted average over it, and then finally calculate the value of y at the next time step. So, here you would in the improved Euler you were doing one Euler step, then taking an average over the slope here and the slope here, the value of f x y at this point and at this point. In Runge-Kutta, you are going to do this step multiple times. You are going to calculate it over different points over the interval. So, this is the basic principle, so that you have a better average, a better estimate of f x y, the average value over the interval. Okay. So, the derivation of Runge-Kutta, why and how it is accurate to h to the power 4, you can look up the book of Hasburn and De Vries, which is already listed, but here we shall more focus on the implementation of the code. Just like RK4 is accurate to h to the power 4, you can also have RK is 8, which will be more accurate to order of h to the power 8, but then you have to basically average over this f x y over larger number of points. Okay. So, let us go to the details of the algo, and what you have to do in RK4, of course, start and calculate the f 0 at x 0 y 0, that is the initial point. You have the function, put in the values of x 0 and y 0, calculate the value of f 0. After that, you have to update the value of x 0 and y 0 by an interval h by 2. So, that you calculate a temporary value. This is not your final value, this is basically an exploratory value, you are just doing an Euler step. So, y temp 1, so some new value of y, but it is a temporary variable, hence I have called it y temporary 1 because we are going to do this multiple times, equal to y 0 plus f 0 x which is calculated at x 0 and y 0 into h by 2. Note the interval is half the interval, h is the total interval. So, you want to calculate the value of y finally at 0, h, 2h, 3h, 4h and so on so forth over the entire range over you want to calculate over. But here you are doing an Euler step over half of the interval. So, you have an estimate of what the value of y could be, right, at half of the interval, and with this point, with this y temp 1, this estimate of the value of y, you again calculate the function f, okay. But now I am calling it f1 because previously when you calculated it at x 0 and y 0 I called it f 0, but now at f1 because you have a temporary estimate of y temp 1. So, using that, right, and x 0 plus h by 2 you calculate f 1. Okay. Now, using this f 1 you again update the value of y. So, this is again an temporary estimate, right. So, you are starting out with, so from here you basically try to have an estimate at the interval h by 2, then you calculate the f x y at this point which you call f 1. Now, with this f 1 again you make an estimate. So, previously you used this f x f 0, now you are using f 1, this average, a better estimate of the slope to again get an estimate of y 1 over an interval h by 2 starting from here. So, what you are doing is y temp 2 is y 0, again the initial point, plus h by 2 into f 1. Okay. So, you have a second estimate for what could the value of y be at an interval, after an interval h by 2. Using this y temp 2, again you calculate the local slope, the local value of f. So, you are calculating f 2 x plus h by 2. So, the value of f 2 at x plus h by 2 and y 0 plus h by 2 f 1. So, this has been calculated here, this has been calculated here. Now, you are updating this value of f 0. So, you are basically calculating the slope at different points in the interval, getting better and better estimates, right. With this f 2, you again calculate an estimate of the value of y. This is not your final y, it is an estimate of the value of y. So, y 0 plus, now you see that basically the interval is now over h, but this is not your final y, this is still an estimate. So, we are using this f 2, right, which was calculated here to update y, to have an update of the value of y. This is again temporary. So, this y 0 plus h, the interval is over the entire interval, right. So, basically what you are doing, using the value of f 2, you are trying to have an estimate of the value of y over the entire interval. So, somewhere here. So, similar to improved Euler, but now you are using better estimate of the value of f x y, right. So, your actual value, the final updated value of y at x 0 plus h is y 0 plus h by 6, right, and weighted average of f0 plus 2f1 plus 2f2 plus 2f3. So, f0 is the one calculated at right at the beginning, then you using f0 you updated the y1 by h by 2. Using this y1 using this new y temp 1 you calculated f1 right here at interval h by 2. Now, using this slope, using this f1 you again updated y1 you again updated y over an interval h by 2 to calculate y temp 2. With this value calculate f2 and you are storing your f0, f1, f2 each time. Using this f2 update another temporary value of y, but at interval h, right, and then at that point calculate f3. So, you basically at different values of y you are having an estimate of f, you are taking a weighted average and this is your final y. Taking this you can again calculate it at y at x plus 2h, but again you have to do these 4 steps. So, this seems to be much more involved than your improved Euler, where you had to do 2 steps. Here you are doing 4 steps, but what you gain, right, though this is computationally more expensive, what you gain is you can use higher values of h. So, suppose you had to use for a particular complex function which fastly varying fxy, a complicated fxy, you had to use suppose h equal to 0.01, right, and you would get an accuracy in the improved Euler case of h square, right, whereas here you have an accuracy of h to the power 4, which is much better, right. And so, even if you use h equal to 0.1, you have the similar accuracy or rather an more accuracy, right. So, h, if you took h equal to 0.01, then your accuracy with the improved Euler would be 0.0001. So, like h square, whereas for improved with Runge-Kutta, even if you use h equal to 0.1, so you are using a large interval, you would have a similar accuracy. So, you are saving around 10 updates in the Runge-Kutta. You are just going from steps of 0.1. How would you implement it? So, basically I am showing the raw code and you should just try it out, and this is suppose x0 equal to 0, y0 equal to 0, we use the same function which is 1 plus y square, right, and suppose you want to integrate it from 0 to 1.55 or 1.54 just like that, and you want to plot the function, the solution of the differential equation. So, h equal to 0.02 say, and write 22 the initial values. So, the value of x and y, right. Later you are going to plot x versus y. So, you will have at different values of x different you will basically write down and calculate and write down different values of y, and you are going to plot x versus y. That is what we did yesterday. So, here do I equal to 1 to number of iterations. Suppose if it is 1.55 or 1.54, then you can calculate the number of iterations will be 1.54 divided by 0.02. So, that is your increase in step size. So, f0 calculated is 1 plus y square. Using that I am updating x0 1. So, I am calculating x1 essentially here, which is x0 plus h by 2, and then updating y here, calculating f1 here using this value. We are not using x1 in this function, but you could have a function where you have to use x1 as well, which is updated to x0 plus h by 2. Now, using this f1 you have to update, again you are updating x2, but starting from x0, it is at this interval h by 2 which we are not using, and updating y here right. It is the same as this line, starting from y0, and we are updating this. Then we calculate f2, right, using this value of y temp 2 that we have calculated. Then we calculate in the next step, using f2 we calculate y temp 3, which is nothing but this step, and also update x3 equal to x0 plus h, though we do not use it to calculate f in for this particular function. And finally, your final corresponding to this step is y0 equal to your new value of y0 is y0 plus this weighted average, right. Update x0 to x0 plus h. So, write down, suppose in some file 22 x0 and y0, and this goes on and on. So, x0 keeps on changing from 0, 0.02, 0.04, 0.06, 0.08, and every time using this step you have an updated value of y0, the value of y0 at 0.02, 0.04, 0.06, 0.08 and so on and so forth, and use this to do the entire stuff. So, this is your new value of y0, thereby you can, doing these 4 steps, you can calculate y0 at x equal to 0.04, right. So, we shall end this class with a discussion of the errors involved in each of these methods. So, in the Euler method, if you remember that we are neglecting terms order of h square. So, d2x d2y dx2 into h square, the higher order terms, the second order terms we are neglecting, right. So, in each step, we are neglecting errors of h square. So, that is the error that is being introduced. So, in each step when we calculate the new value of y, right, we neglect this step, and so this is the so called local truncation error in each step, right. That is the order of that is the and it goes as h square into d2y dx2. Of course, at each point when you integrate each point, when you calculate the value of y at each point, the value of d2y dx2 will be different, but the prefactor remains h square, and so thereby the local truncation error is h square. However, to calculate the global truncation error, that is after n steps of when you have basically calculated the value of y over n steps, h plus h plus h plus h after n h steps, what will be the total error? Now, in each step you are making an error of h square d2y dx2, but now you have to sum over all these errors over n steps, right. And when you multiply n h, basically the error becomes the global truncation error over the entire interval becomes h into d2y dx2, where d2y dx2 ideally should be at each step, but I have written it as an average over different steps. But the global error becomes the difference in interval x n minus x 0, because you are summing it n h if you like into h into d2x d2y d2y dx2, right. So, the error over the entire interval goes as h, this is pretty high, right. But if you halve the value of h, your global truncation error will also reduce by half, because basically when you have summed over it, this is n into h is this entire interval and h remains, and so on and so forth. Now, you can look up the book for the derivation of improved Euler, but in improved Euler, the local truncation error, the error made at each step goes as h cube. For Euler it was going as h square, for improved Euler it is going as h cube. And when you sum over the entire interval, when you sum over the errors over the accumulated errors over the entire interval, it goes as h square. And Runge-Kutta was giving such good results even for relatively high values of h, because For the Runge-Kutta, the local truncation error goes as H5. Again, why H5? I mean, that is why you call it RK4, but the derivation is there in the books. Here we are focusing more on the implementation, it goes as H5. And the global truncation error, just as before, goes as H4 when you sum over the errors over the entire interval. So, of course, it is the margin of error. Here it goes as for Euler goes as H, for improved Euler global truncation goes as H square, and in RK4 you see much more accurate values, closer values to the actual function, even with higher values of H. So, with that we come to the end of this lecture. We have basically discussed Euler, modified Euler, improved Euler and Runge-Kutta. For practical purposes, you shall always be using Runge-Kutta. So, next class what we shall discuss is how to do coupled equations, the simple coupled equations, and then we will slowly move to the nonlinear case. How do we go about it? Thanks.